In this video, we're going to go over problem 3.97 from the book. This problem, we're given a force applied at A. The magnitude is 46 pounds. And we're also given a moment applied at A. We can also think of this moment as a couple. So the moment and couple, the magnitude is 2,120 pound-inches. And we're given a line of action both for our force and our moment, because they're both vectors, so they can be drawn with direction using our line of action. The problem asks us to find the equivalent force-couple system at H. I'm going to start this problem by breaking the force and the moment into its different components. So to solve, I'm first going to break F into components using the line of action given. So F is going to be the magnitude of F, which is 46 pounds, times the distance. We go from A to J in the X direction, which is 18 inches. The direction we go from A to J in the Y direction is negative 14 inches. And the distance we go from A to J in the Z direction is negative 3 inches. I'm going to divide all that by the magnitude of the line of action, so 18 squared plus 14 squared plus 3 squared. If I work that out, I get my different components to be 36, negative 28, and negative 6. I also want to break our moment or couple into its components. So if I look at this M here, it's going from A to C is my line of action. It's a vector, so I'm going to break it into the components the same way that I broke my force into components. So I have M is equal to the magnitude of M, which is 2,120, times the distance from A to C in the X direction, which is negative 45. The distance from A to C in the Y direction, which is 0. And the distance from A to C in the Z direction, which is negative 28. I also need to divide that by the magnitude of the line of action, which is 45 squared plus 28 squared. If I solve this out, I get negative 1,800, 0, and negative 1,120. So let's go ahead and draw what this looks like on this object. So we have this long rectangular prism. It's not great. Let's draw our axes in here. We have our X axis here, our Y axis, and then our Z axis. And at point A, which is here, or let's go ahead and put in our dimensions. So this is 14 inches. This is 45 inches. And this distance here is 28 inches. So at A, we have an applied force that goes positive 36 in the x direction. It goes negative 14, or sorry, negative 28 in the y direction. I was reading the wrong thing, negative 28. And it goes negative 6 in the z direction. So that's what my applied force looks like, but I also have an applied moment here. So in the x direction, my moment is pointing in the negative x direction, so that's this way. We typically draw our moment vectors with a little curve around them to show that it's a moment. And that magnitude there is 1800. And we have a component in the z direction, negative z direction, going 1120. And what we're looking for in this problem is to replace this applied force and applied moment at A with the equivalent force couple system at H. So we can picture we have new axes over here at H. We have, HX, HY, and HZ. And we're looking for the force and couple that will have the same impact on this rigid body as our original loading. So if we think about this, the equivalent force is going to be the same or have the same components as the original force. So our equivalent force at H will have those same components, because if we want the force to have the same impact on the object, it's going to have the same x component, the same y component, and the same z component. So our force at H is going to be 36, negative 28, and negative 6. Our equivalent couple or moment at H will be a little bit more complex to solve for. Because we're moving the force from A to H, we have to consider the moment that the force at A creates about H. So when we're solving for this moment at H, it's going to be the moment at A, which is those two components, the negative 1800 in the x direction, negative 1120 in the z direction. But then we need to add the moment that FA, the force at A, creates at H. So let's go ahead and calculate that. So we already solved for MA, negative 1800, 0, or let's solve for this in components. I think that's going to be more straightforward. So MH at X is going to be the moment at A, so negative 1800, plus the moment that this force here creates about H, X. So if we look at the X component of the force at A, that won't create a moment about HX. The Y component will not create a moment about HX because that Y component goes straight through the axis. but the z component will create a moment about hx. It's going to be a negative moment, so it's going to be negative. The magnitude in the z direction is 6, and our moment arm there is 14. Then to solve for the moment about hy, we have the moment at A, which is 0. And then our Z force is the only force that will create a moment about HY. So we have plus 6. Our moment arm is going to be 45. Lastly, we have MHZ. So it's going to be the moment at A, which is negative 1,120. And the moment, or the force that creates a moment about HZ, looks like we have 2 of them. So the X force will create a negative moment. So we'll have minus 36 times a moment arm of 14. And then the Y force also creates a moment about that axis. And that's going to be negative 28 times our moment arm of 45. So we can solve each of these, and we get negative 1,884, 270, and negative 2,884. So the moment at H is going to be negative 1884, positive 270, minus 2884. And those units are pound, inches. No, our units for our force up here are pound. So the equivalent force is this here. Our equivalent couple is this. And if we applied this force and couple at H, it would have the same impact on the rigid body as our original loading.